All right, let's take a look at what makes the earth shake, rattle, and roll. And that would be an earthquake. And they can do some funky things. They can break rocks. This is more of a really compressed rock. It's a metamorphic rock. You've got some bending that goes here. We'll talk about that in a little bit too. But this shifting right here, where this is actually offset and raised up, that could be signs of an earthquake, of a fault that was moved up or one that fell down. So what is an earthquake? I mean, that's just the basic principle, right? What is it? Well, it's a sudden movement or shaking of the earth. That's the definition of an earthquake. It's caused by plate tectonic stresses, usually found at plate boundaries, resulting in the breaking of Earth's crust. Now, there are some other things that can cause earthquakes, like hot spots in magma chambers, but for the bulk of our earthquakes, they're at plate boundaries. And that was actually how we figured out where the plate boundaries were, because during the Cold War, we wanted to know what kind of atomic bombs were being set off by the USSR. So we, set up about 120 seismographs around the world to kind of pay attention, because that can tell you how deep and where something is by those waves that come out. But because they put all those sensors out for spying purposes, they had a geological impact in that they discovered that earthquakes really are found in these narrow bands, and that's at the edges of tectonic plates. So it actually helped prove a theory that had been around for a while of how plates moved. And that theory was by Alfred Wegener. He came up with the theory of moving plates. So you can see that down on here. You can actually see outline of different plates. Here's the Pacific plate, the Pacific Rim. It's the Ring of Fire, because those are usually pretty good subduction zones. We've got the North American plate here, the Nazca plate, the South American plate, the Antarctic plate, the African plate, the Eurasian plate, the Indian plate, and there's a few other small ones that, the Australian plate, that honestly I think I need more powerful glasses to read without making that a little larger. So I wouldn't test you on that. You just need to know they exist. So there's really three different ways that tectonic stresses can build up. It can happen where we're spreading apart, where we're getting smashed together, like subduction, one slides underneath the other one, or where you're moving side to side, which would be like the San Andreas fault. So they have specific names that we'll learn by the end. Those and the stresses they cause would be really good questions on a test. In fact, I can guarantee that they will be on. Plate boundaries and faults cause frictions as plates move. Okay, plates and fault zones have basically a stick and slip motion. They get stuck and then they release. Then they get stuck and then they build up energy pushing behind it, and they release and they slip. So that stick period, that part where they stick, there's no plate motion. It's storing up energy, kind of like when you pull a rubber band really far back. In fact, ironically, I have one here. So when I pull this back, I'm literally storing the energy. And if I let this go, I'm pretty sure it'll hurt my thumb, so I think I won't do that. But in that sudden release, that's your earthquake. It's that sudden movement of all that stored energy. So no movement, we're storing energy. When it slips, it's a sudden fast motion, and that's the kinetic release. Kinetic energy just is the fancy way for saying movement. Potential energy is stored energy. Kinetic energy is the movement. So the sticking period is the potential. The slipping period is the kinetic. It's the actual release of energy. So we can start, look how nice all those little rivers are all flowing up, and it can get uplifted, or it can actually get shearing, go side to side, or it can get fall down. So those all have names. San Andreas is a strike slip fault. They go side to side. So really, really good diagram to write in your notes. Now, I don't make you take notes, but I'm also telling you that you can take as many notes as you want, and you can use them on the test. And you're going to want this on a set of notes, so you have a quick reference. All right, so if I have a place where I have movement, it's either going to slide down the hill, get pushed up a hill, or it's going to go side to side. All right, So a normal fault is like a slide you'd slide down when you were a kid, or now if you still happen to enjoy that. You've got your inclined plane and the other plate slides down. That's a normal fault. And that's usually where you have stuff being kind of pulled apart, so it has the ability to slump down and pull away. Now, if it's under compression, I can have a reverse fault where this footwall has the hanging wall slide up, and it's reverse of normal, so we call it, guess what? A reverse fault. A normal one slides down, a reverse one slides up. And the wall that either slides up or down is called the footwall. The hanging wall is the one that hangs and either moves up or down, just like a picture on the wall. And then we have something called a strike slip fault. That's the San Andreas, it's side to side. And that strike slip fault is a shearing force. So reverse fault is under compression, they're getting pushed together. The hanging wall slides up. But in a normal fault, where the hanging wall slides down, that's actually under tension. It's being pulled apart. Let's say you wanted to be really, really mean, and you hook someone up to a horse on one end and the other end on another horse, and you wanted to split that bag of flour in half and have the horses go. That's going to be under tension until it breaks, until it pulls apart. And that's a normal fault. So normal faults, hanging wall slides down. Reverse faults, hanging wall slides up. And strike slip fault, we have side to side. Now, normally if we were physically in the classroom, I have blocks, you play with this. What you can do is literally take a piece of paper, draw a line on it, okay, and then cut, like shade in one side, draw a cut line here and cut it apart, and you can actually mimic all of these things with a pretty simple piece of paper. And so let's take a look at what that would look like. These would be the blocks we would use. So here is where we have our blocks all lined up, okay? And if we look at it from this point of view, assuming that the bottom of the picture is down, and in this case the blue is down on top and the green is on the bottom, this one right here would be the slide. The slide would slide down, right? Because it would be hard to slide up this way, but you could slide down the one on the right. And so this would be my footwall, and this one is my hanging wall. Now this one, it slid down, the footwall, the hanging wall slid down. So that would be a normal fault, okay? Because it's sliding down. Now this one, if this is the footwall, and here's my slide right there, and it slid up under compression, that would be a reverse fault. It's going the opposite direction of what they expect. Now, pretend this one is laying flat on the ground and it's moving like this. That would be a shearing stress or a strike slip fault. That's your San Andreas. So this one falling down, tension. This one getting pushed up, falling down. This one getting pushed up is under compression. Or you think of this as one continent sliding underneath another one, pushing this one up, and this one's getting subducted. This would be then kind of like your Pacific Ring of fire, where you have volcanoes because of subduction zones. This would be like your mid-Atlantic ridge, where the Earth is splitting apart. It's under tension, it's pulling apart. So let's try some things and look at some pictures and see if we can identify. This would be also good things and tests to give you to say, okay, let's look at some pictures and can you tell me what kind it is? Well, this is looking from an airplane down, and we can tell, see how this is kind of lined up, but look, this is a little bit off, and look, these aren't lined up with anything over here, is it? And this plate is moving to the right, the one on the bottom is moving to the left, which means, ladies and gentlemen, that this used to be one of these, probably these two over here by the definition. These are a little more subtle, kind of probably with those. So these two, or maybe these two, used to be over there. It slipped a long way. So this would be a transform fault, or a what would you call it? Go back up here if you can't remember. Strike slip fault. That's the shearing force. Sometimes we call them transform faults. I would use that term interchangeably with strike slip, but you should understand it's like shearing. And if you go back in the notes and look at this, I actually tell you underneath what it is for these first couple. All right, let's look at the next one without looking at the answer, see what we can identify. All right, so look here, we see that we've got this black layer here and here, and we have a black layer here, and that kind of looks like it used to be up there. Look how wide that is compared to that one, and this one isn't nearly as wide, so this thing really fell down, didn't it? So we look for where our slide would be. Where you would slide down the rock, the fault line, that's your footwall. This one moved from up top down below. It slid down the footwall, so the hanging wall moved down like a normal slide, so that's a normal fault. It's under tension. This one, now here's where my slide is, right here. And if we look at this, here's a white layer down here on the left side, and that white layer has moved up on the right side. So the hanging wall is sliding up the slide, going in the opposite direction of normal, so that's our reverse fault. And that would be under compression, getting squeezed together. All right, take a look at this one. I do have these in the notes. I'm not actually going to make you go and answer these questions, but we're going to answer them now. So in your head, tell me what kind of fault this is. Is it a strike slip? Is it side to side? Is it normal sliding down? Or is it moving up? Well, if we line it all up, this is my slide on the left and it's moving up the slide, so that would need to be a reverse. All right, let's look at this one. We're going to pretend that this one is flat. This is like the San Andreas, so it's not really moving uphill. It hasn't gotten any higher, hasn't gotten any lower. It's just moving side to side. So what kind of fault is that? Strike slip, normal, or reverse? And that would be your strike slip. It's a shearing force. So here's just a quick review. Compression forces pushing from opposite sides, squeezing. Tension forces pulling from opposite sides, shearing stresses, that is sliding past each other in opposite directions. And the confining stress is one more we're going to add in here. We haven't really talked about it. It's a subtype of compression stress caused by the weight of the rocks above. So sometimes you can have a little bit of movement on the bottom, but up on top it's not really, well, or you could have a little bit of movement at top and it's so much weight down here, it's kind of like adding a second layer of stress. It's going this way, but it's also getting pushed down, so it's being confined. So a subtype of compression stress caused by the weight of everything above it, causing it to move at the top and the bottom at different times, which means if one's moving slightly and one's not moving at all, that's building up more and more stress before it slips and you get a pretty good earthquake. So let's look at this one. It's going the opposite direction of the way we've had some of our slides go, so doesn't matter. I mean, a slide can go in any direction, right? Let's notice the layers of rock. So here's my black rock, and here's another line of it. Here's these darker rocks. This kind of looks like a sandy area that probably lines up somewhere in here, but really I think you have to go even farther, because I think this sandy area lines up with this sandy area, and this one down here goes way up there. So this side here, this is my footwall. That's the slide I'd slide down. And it looks as though the hanging wall is sliding down. So is that reverse normal or strike slip? If you said normal, you're doing really well. All right, now let's get into more of the mechanics of the earthquake itself. Now, so this is where one of those forces moves. It either slides down, it gets pushed up, or it's going side to side. And when that happens, that release of energy causes an earthquake. So earthquakes basically occur because stresses build up between the plates as one plate passes another, so side to side, up underneath it, or pulling apart. As the plates move past one another, they don't do so smoothly. Rather, they snag and grind, allowing energy to build up. Now, that's not true. There are places on the San Andreas that really don't experience any earthquakes because they have almost like this chalk, and their rocks just kind of actually do slide past one another. So it's a real smooth, but you can actually see the movement. I mean, their curbs are not lined up. Their fences, they have horse fences or other kind of fences, aren't lined up. So you know that it's moving, but they don't have the big earthquakes. But farther up on there, where they don't have that chalk-like substance, they do build up stresses and they have bigger earthquakes. And that's one of the videos that we'll actually look at. We'll talk a little bit about that. So often the focus is where the break occurs is underground, and that focus is the actual point of the breaking of the rock. The point directly above it at the surface, where all the surface waves are going to radiate out in all directions, that's called the epicenter. And that's the epicenter, is the center of where the surface waves are radiating out from. Seismic waves have different names. Surface waves, primary waves, and secondary waves. And those are, guess what? Abbreviated as S wave, P waves, and S wave, or P and S waves. And two of them can travel through the earth, and one travels along the surface, but one can't travel through liquid. So we'll talk about that in just a minute, why that's important for us to know. But good test question. The focus is where it occurs underground. The epicenter is the point directly above the focus at the surface. So you'll notice that here is my footwall right here. Here's my hanging wall. It looks like it slipped a little bit down, so this would be a normal fault. And the center of the break occurred down here, where enough tension finally gave and it moved. And so often your fault line might look here, but it doesn't necessarily mean it's going straight down. It can go sideways, it could be going the other way, it could be going straight down. It just depends on where it is at that point. So when the plates eventually move again, this energy is released as shock or seismic waves through the Earth's crust. And the point at which the slippage occurs, again, is called the focus, whilst the point above ground is called the epicenter. Seismic waves, shock waves, will emanate rapidly outward from these points, and their energy will reduce with distance. It's kind of like the moon. We found out from the moon landings actually has moonquakes, but because there's no water to absorb the shock, where it lasts for seconds here, it can last for up to an hour on the moon, because the rocks just keep letting the waves travel through. Where on Earth, all that water kind of deadens some of the intensity to absorb some of the wave. So earthquake intensity has a measurement scale called the Mercalli scale, or modified Mercalli scale. And basically, here's what we're going to go. Here's the deal. You don't have to memorize this scale. But if I gave it to you and said, what level would this be if this occurred, I expect you to be able to use the scale. So on the modified Mercalli scale, 1 is not felt. A 2 is felt by only people at rest. A 3 to a 4 is felt by people indoors only. A 5 to a 6 is felt by all. Some damage to plaster chimneys. A 7, people are running outdoors. Damage to poorly built structures is going to occur. An 8, well-built structures will have slight damage. Poorly built structures will suffer major damage. A 9, buildings shifted off foundations. A 10, well-built structures destroyed. An 11, few masonry structure remain standing, bridges destroyed. And a 12 is damage is total. Waves seen on the ground, objects thrown into the air. We see up to 9s. I don't know that I've ever seen an 11 or a 12. I'm not saying they haven't happened, but in my lifetime I can't remember one. We've had some 9s, and those are pretty massive. So my cousins, 2 of them live in California, and they come here and are terrified of earthquakes, but don't really care. They're not terrified. They're terrified of tornadoes. Earthquakes they've lived with their whole life, so it doesn't bother them at all. My sister used to work for Northwest Airlines and now does Delta, and she was in management, so she would actually, when it was still Northwest, would have to go to Japan about once a month. And she said they have earthquakes so many times a day that unless it was massive, they didn't think anything of it, because it just is part of their daily life. So it's all a matter of what you're used to. We know we have tornado drills. We practice for that in school. You know where to go if you're in your house. Shopping malls have tornadoes, shelters. My cousin in Washington State, they didn't have tornado drills. They had evacuation drills. in case of, well, like a tsunami, which isn't as big of issue, but it can happen, or, well, a volcano exploding. And it's evacuation because they have indication that one of like Shasta or Rainier or Mount St. Helens or something like that was going to go. And they actually practice evacuation drills where they get on buses and they get the kids as far away from those mountains as they can. So we have tornado drills for the same reason they have, other drills for what their natural issue is, which if on the Pacific Rim would be earthquakes. So you can actually show, if here's the epicenter, you can see the waves dissipating. It might be an 8 here, but then you've got this ring of 7s, and around that you've got a ring of 6s, but look up here, there was actually a few 9s, so there must have been something that really slipped there, but down here it was 8s. So you can actually see a progression of dissipation of waves. It doesn't mean that this isn't going to still be felt, but this is where the worst damage, and that would have been where the worst damage was. All right, so let's talk about those waves. So from the focus where the break occurs underground to the epicenter right above it, surface waves radiate out. But actually, do you notice that they're radiating out in all directions? It just depends on where they flow is what we call them. So the epicenter is the geographic point and the surface directly above. Now, do you think I've said this enough times that you should know the difference between the focus and the epicenter? It's a really good test question. Seismic waves produce by that release of energy. They move out in circles from the point of the rupture, from the focus, that point underground. So there are 2 types. There's surface and body waves. One travels on the surface, one travels through the earth. P waves are that back and forth movement of rock. Now picture taking a slinky and having one person on each end of it sitting on the floor, and you literally pulse it back and forth, or you go side to side. This is what we would actually be mimicking. So when we look at those, we can kind of start to see how waves travel, because some kind of roll, some are compressional back and forth. So S waves have sideways movement. So this one, the P waves, if you pulse it, you literally push, you can actually see the slinky waves bunching up, moving to one side and reflecting back. S waves are literally, you take one end of the slinky here and one end of the slinky here, and you shake one side and you can see the S wave pattern start to occur. And they happen to be primary waves and secondary waves, but it also happens to know that these pulse and these go side to side. And those waves that you're talking about when you're looking at slinking going side to side have crests and troughs, just like any wave. So a light wavelength, a sound wavelength, or in this case, an earthquake wavelength, you have amplitude from the center where it radiates top and down. That's amplitude, from the center to the top and to the bottom, and that top is called a crest, and the bottom is called a trough, and from crest to crest is called a wavelength, or from trough to trough is called a wavelength. Good test question. You need to know the basics of a wave, because you need that for my class next year, and many others coming up. So earthquakes, we record them with a seismograph, which is basically, this is attached to the ground. This is usually a free hanging weight, suspended. Now sometimes it's off to the side, and this one's up and down, and usually has a tip of a pen touching paper, and that paper will move underneath it. And sometimes they'll use sand, but that would be a really, really old kind of one, because we want to have a better record of that earthquake. And so it can tell us the amplitude, the height, that from the center to the crest, or the center to the trough, tells us basically how much rock moves or vibrates. So the amplitude of the wave tells us the intensity. We can also find out the distance to the epicenter and the direction from which it came. All of that from a handy dandy seismograph chart. So earthquake waves, 3 types: P waves, S waves, surface waves. P waves shake the earth in the same direction as the wave. They travel through solids, liquids, and gases. Okay. S waves shake the earth side to side, and they travel through solids only. These are not going to make it through the center of the earth. Surface waves, guess what? Travel in circular motion, kind of like that rolling motion along the surface, and these are the ones that cause the most damage. This would be if you try and take the slinky, you'd actually have to shake it up and down trying to get that motion. It's a little harder to do, but it makes a lot of noise if you want to try it. So S waves, secondary waves. They cannot travel through a liquid, so they can't travel through the core of the Earth. P waves, compressional back and forth, can travel through solids, liquids, and gases. They get deflected a little bit, and that tells us where they exit the other side of the Earth, helps us triangulate where that is. And if you're triangulation, basically, if we can take 3 different seismographs from around the world, we can actually determine the epicenter, the focus, where it happened. If you've ever been to the Science Museum and you've heard there's this huge xylophone up over the cafeteria area, and if you've ever heard it go off, that's actually a seismograph. The tone, the more intense the sound, the louder it is, the more intense the earthquake. The duration is how long it lasts. And I can't remember if it plays different tunes for different directions. That one you'd have to look back up. But I do know that it's a pretty cool thing. If you get there and you ever hear it go off, it means there's an earthquake somewhere. All right, this is what I was talking about with this slinky. Back and forth. Basically, here's your spring. Push it back and forth, and you see the clumps moving through, and it will bounce back and reflect to you. S waves, side waves, literally shaken side back and forth. So if we see this wave traveling through the mantle, and then traveling through the outer core, which is liquid, we know that has to be a P wave, because S waves can't. It would actually get deflected back up. So let's take a look at this. I don't need any sound, but we're going to watch an earthquake occur and see what happens and look at the waves as they go. So here's my earthquake. Here's my waves going out. There's my surface waves traveling. See, my S waves only travel up here, but my P waves can travel through the liquid. And see how they're slightly bent? And then they almost kind of mimic that curve. It gets reflected back up. Surface waves are still traveling. So if we have a seismograph here, a seismograph here, and a seismograph here, you'll notice that the surface waves arrived at those locations at different times. And that time increment between where it hits each station, whether it's a surface wave or these S and P waves, helps us determine through triangulation where it is and just how intense it is, because the stronger the quake wave, the stronger, the farther those waves can travel, because they dissipate. L waves can also, these are surface waves, can be broken into 2 parts. Raleigh waves and Love waves. Guess what the names of the people were who figured these out? Raleigh and Love were their last names respectively. L waves feels like an ocean wave, that up and down, that bouncing, that if you ever go out far enough into the ocean, you actually ride the waves, you'll actually just go up and down and up and down and up and down. You really won't come into shore unless you get into shallower water. Where your Raleigh waves travel along the surface only, we get some really interesting things. I expect that you've heard of these surface waves, P waves, S waves. That's what I'm going to make sure you know for the test. Here again are more ways to go through if this helps you look at it. It just kind of shows you the vibrations traveling through. This is kind of that side, and this is that rolling up and down with your S waves. And the compressional, you can see a little bit of compression here, here, and here, and those are your P waves. So whichever way works the best for you. Remember, these notes are available in the folder at the bottom. You don't have to go through the video again. But here is a copy of a seismograph. P waves arrive first, S waves arrive second, and we can actually use the distance between those 2 things to figure out scale and how far away it is. And then we use that and compare with others. Normally we would do a lab. We're not going to be doing that today. Here is another modified Mercalli scale. This is the old traditional Richter scale. Basically, generally not felt but recorded on seismographs as a 2.5. That would include 1 and 2s here. So they just kind of break it into more specific parts. This is probably going to be the scale you've heard more of, but this is the one that's probably a little more widely used. See, this 3.5 is actually broken into 3 parts. Some local damage may occur is broken into 2 parts. A destructive earthquake here has got 2 different separations within that scale. A major quake is a 7, is a 10 here, and 8 and up really big earthquakes are broken into 11 and 12. Again, not going to make you memorize that, but you do need to be able to read it. All right, S and P wave interval does tell us some timing information on a seismograph. When this first starts to go, that's where we do this first line, the arrival time of the P wave versus the arrival time of the S wave. Surface waves are way back here. So on one graph, you will actually see the primary waves, then the secondary waves, and then the surface waves hitting. If you wish to watch this, you are certainly welcome to there in the notes. It's a little bit of Bill Nye looking at a seismograph. I'm not going to show that on here, but you are certainly welcome to go back and look at it. Now, sometimes when you have Earth move and you have earthquakes, you start to get more compression and things start to get squeezed together. And this is a little precursor when we look at mountains. You can actually have a folded mountain. Basically, take a long sheet of, like, let's say seafloor that you have layers of sandstone and siltstone and shells and all these different layers. They're very discernible layers. And law of superposition will say the oldest stuff's on the bottom, the newest stuff is on the top. But if they're under compression and get squeezed together, they can actually get folded. Like, you know, a piece of paper. I can fold it with rises and falls and make it go from this wide to, you know, that wide. So, no, that was my budget info for science. I've got to get stuff purchased. And those folds have specific names depending on the direction. At the top, it's called the anticline, like an incline, right? Except the incline is at the top, the anticline. The syncline, the slide where you slide down, is the bottom. So synclines are on the bottom, anticlines are on top. So if I looked here, knowing where gravity's pulling me down, this points up like an A for an anticline. This you slide down to the syncline. I will show you a picture like this. May not be this one, maybe this one. I can't remember which one I have on the test right now. But you will have to identify if this is an anticline or a syncline, and if that's an anticline or a syncline. See, all these layers have actually been folded. This is a folded rock. You can have whole folded mountains. And you can see right here, here's your syncline way down here. And so this would be older, but then it can get flipped and turned over, and you can get all sorts of weird things happen when you put enough heat or pressure and compression under it. Look here, we've got the top of an A. So here's an anticline. It goes down to the syncline and then slightly raises to an anticline and drops down to another syncline, rises to a higher anticline. So you can see if you go out fishing, if this I think is the Canadian Shield, if I remember correctly, you can see stuff like this out in nature. Now let's talk about the damage earthquakes can do. So this actually split apart a little bit, but it looks like it got lifted up. But this one could have slid down. So unless I have more information, I can't tell you if this is a reverse or normal, because I would need to know which side moved. Did it move up or did it move down? This one, so that would either be a normal or reverse. This one actually moved sideways. You can see literally it's bent. It didn't go up, it didn't go down, it just got bent. So this would be like the San Andreas. This would be your transform or your strike slip fault. Again, the same thing here. Look, these crops were originally in a straight row. The earth shifted and the rows are no longer exactly straight. So earthquake damage can cause landslides. It can cause buildings to be damaged, but it can also cause this thing called liquefaction. You guys have experienced liquefaction if you've ever stood at the lake as the waves lap in, and you just stand on the sand and all of a sudden you kind of start sinking down, because that movement makes all the water molecules start to move, and water isn't a very good supporter of solids, and you sink down. Well, if you build a house or a structure on waterlogged sand, it's pretty stable until you start to shake it. Then the particles start to flow out, leaving the water behind because you can't compress water, and stuff sinks down into it, and that's liquefaction. This was normal. This slipped down, so this is under tension being pulled apart. This would be a normal fault because it slipped down. This is a landslide that occurred because of an earthquake, and they lost basically a whole house. Earth is a pretty powerful thing. This would be your strike slip fault. It's moving side to side. It bent the tracks. This one slid down, and literally this building got split in two because this half was on one side of a fault line and this was on the other, which is a nasty way to find out you have a fault, is when you lose half of your building. Basically, an entire floor. Look, this upper floor is now lined up here, is now lined up with the ground floor over here. And in case you're wondering, all of that striking and slipping together gnarls and gets scrunched up, and you can get this jagged scar. And this, ladies and gentlemen, is the San Andreas Fault. This isn't as scarred, but it's definitely shifted because this fence has shifted to the right and this one has shifted to the left. So we know that's like the San Andreas. In fact, actually, that is the picture on the San Andreas. Strike slip because they're offset, they're not up or down. And look at this. Here is a really well-defined creek bed. Look at that. And it's completely shifted. These are no longer lining up. Here's one no longer lining up. It's definitely shifted. The bottom has shifted to the left. And look at this. This is orphaned creek bed. It was somewhere else. It's got two strings coming in. Probably this one and this one. It is shifted that far. But look, here's a new trail that's been worn in. So that one is pretty fresh. But from a plane, you can see where it moves. So let's get back into that liquefaction. And there's a video on it, so that's what I'm going to expect you to do. It's when soil and water, or sand and water, becomes saturated and acts like a heavy liquid. Liquids don't like to hold stuff up. So it results in the loss of strength and the ability for the soil to support it, the weight, and it literally, you fall down. This is liquefaction. Basically, these whole apartment buildings got sucked down. Think of it as like massive quicksand. It's basically what it is. You have all the particles that are normal, then it starts to shake. The water kind of gets jostled up and you no longer have a stable foundation. This is liquefaction as it occurred in Japan. And if you watch this whole center part of the sidewalk will eventually start shifting back and forth. So they were having an earthquake which caused some motion, and then this liquefaction started. And there it goes. See it move? It's really hard to see. If you can, pay attention to it. You can see it moving right there. That's better. And pretty soon, there it goes back and forth. I mean, that whole center strip is sliding. Trees and everything, they're not falling over. This light post is not falling over. The whole thing is just shifting back and forth. How crazy is that? And that's all because of liquefaction. Now, eventually, the water starts to come out, and that is your water being released. It's being shaken out of the ground, kind of like you squeeze a sponge, and you see the rippling there. This is actually moved a little bit. It's still moving back and forth. It's still sliding on the water is basically what's happening. She's panicking a little bit because look at all this water coming up. So she's running onto the center to get around it. She's going to run up into this parking lot thinking that's going to be safer to get away from this water. And she's going to find out that that wasn't, and it's coming from all sides, by the way. So that is liquefaction. Basically, the earth is squeezing the water out of it and allows things to move because of that. Let's see if we can hurry this along and see that little gusher. Oh, no, went too far. It starts making a little fountain coming out in there. Here is another one. This is a crack that opened up. This side fell down. That would be a normal fault. See, they're sliding, going up the slide. Sometimes those holes are big enough. This is not a good thing. If an aftershock came and actually compressed that, you could get stuck in there. That's not where you want to be. Liquefaction literally sucked the car down into it. So this is all a result of the shaking of the earth. And there's really only one way to get your car out, and let's dig it out. Liquefaction. You are done. As always, if you need help, please ask. And if you need clarification, come back and look at the notes or ask me.